going live. I should be live. Let me open the audio to listen if this works. Yep. The latency is really high though. I should change the latency settings and put to low latency. That's to stream settings. Can I change it now? No. So it's normal latency, but the audio works. And let's begin. So, quick introduction. This is the begin. We'll begin in 2 hours. Yeah, this is quite an impromptu stream. It wasn't planned at the beginning. It was just planned something like 1 day ago, 2 days ago. Yeah, 1 day ago actually, yesterday. And I have a friend, the kind of bar club, private club I'm working. The DMX control setup has died. This is the huge console. DMX console. DMX console. Let's name it DMX console, not controller. Console. There's a huge console table and it doesn't work anymore. And I'm trying to debug it for him before it gets sent for repair to the manufacturers of this thing, which could cost a lot or not. So let me share. I'll have to share the link with him so he can also watch it and see your progress or comment what's happening. Okay, that seems to work. I copy the link, I send it to him. And paste. Okay, now he knows that it works. The audio setup is a bit different. Well, there's no one in the chat, so there's no one to tell me current viewers, although there's one viewer. I think it's myself. Yeah, the audio setup changed a bit. It's a bit easier number of cables, but I don't know if the quality is better or if it's good enough. Okay, 0 viewers, so it was only myself in the beginning or something else. I don't know, but there's no 0 viewer. He might join, and until that, you can still watch the restream. So this huge thing, it will be hard to show you with this camera because this console is just too large. Let me do it this way. That's the console. It is huge, and I'm trying to repair this, so I'll spend, I don't know, a couple of hours to see what's wrong. And let me write down what's wrong. Actually, what he said, there was a short circuit on mains, and just after the short circuit on mains, where also this device was, so it was connected to mains using this cable. Weird cable, I think, but I think for audio devices or audio boxes, this is a normal cable. I don't know exactly, but it is connected to main using this cable. I think in the DMX world and in the audio world it's normal. And the problem is now that it isn't recognized over USB. So apparently it still works. It still can be powered on, although there was a short on mains, but the USB is not recognized anymore. You connect it normally to the USB computer, and then the console just as probably kind of a MIDI device for the computer. The computer triggers everything, also using the buttons, and then you have here DMX output to, the proper DMX output with 5 pins instead of just 3 pins. So you have DMX output to send data to the DMX apertures. And this is how we control most of the lights and controls the light show in the kind of club I'm working, or I'm helping. It's not really work, it's more business it's more casual. So, let's write down, cause short circuit on mains input external to device. Symptom, that's not how you write symptom. Symptom isn't recognized over USB anymore. Okay, and that's all I have to work with. So the first thing, independent of what he says that it powers well, I have to check it to be sure that it powers correct, or that there is no problem in the inputs. So for that we will use the multimeter, and let me show you the results of the multimeter. Automation, I think dashboard. Not home, but measure. Up. Let's have the script reading from the multimeter. Okay, now we have an output for the multimeter. Measurement 0. Yeah, we are in the thing mode. In up. Yeah, now you see the multimeter measurements. Can I make it full screen? Here the multimeter measurements, so you can see if we are connected or not to it. So we're in continuity mode. Are we? No, we're in we're in continuity mode, and whenever I press on continuity, you should see a 1. Yeah, and I hear the beep. I'm not sure you can hear the beep, but I hear it. So the first thing I do before I connect to mains, although it should work, is verify myself if it is all right. So I connect the mains cable. Okay, this is connected. Latching cable. And I just measure the resistance. Just resistance. I measure the resistance between earth and the 2 pins. This way. And if it is... And if it is less than 1 mega ohm, it means there's an issue. So live and neutral have no issue, and between live and neutral we have 1 mega ohm. This is normal for switch mode power regulator input, 1 mega ohm of resistance. So we are fine. The input seems not to be shorted and seems to be okay. Yeah, live neutral, that seems okay. So I will still connect it to my although I don't have to, but I will still connect it first to my isolation switch to see how much it draws. And I have no power on the bench. Let me enable power on the bench. Power is enabled. Okay. So these are the plugs from my isolation switch. If I plug it here, I see that it draws around 2 watts, and we have lights. It's probably not easy to see on the camera. Okay, you see the lights, and when you press somehow on the buttons, oh, it's in demo mode. I don't know what this pattern is. I've never used this console, so I don't know what the pattern is and how it should lay out. Oh, is this a code to tell that it doesn't work? I don't know. But we have around, and I can switch it off here. The switch also works power off. So that works. From mains I didn't get any shock using the isolation transformer, so I will use my normal power cable, which also has a power meter. I'll only show you once, and then it will be out of the way from you. Up. If I switch it on, 4 watts. So pretty efficient. I didn't expect so little. So there seems to be an issue. Now we have to test if it really doesn't work on USB. For that, here is the USB outputs for the computer. Actually input. They have a USB outputs. I'm not sure what this is for, if this is for USB sticks or if this is a hub. I don't really know. And to begin, this is not the right way to put it around. And normally you have this etched parts. This should be on top, not on bottom. What it tells me is the circuit board is probably, or the printed circuit PCB is probably here, and they mounted it on top of here. This is why it is reversed. Because if you watch on USB cables, here you see that there is a logo, the USB logo. It is on top. It means that it should be plugged this way. Like on this side there's the USB logo. So whenever you plug a cable, if the USB logo is on top, then you plug it this way. So in this case, that somehow didn't keep the regulation, or didn't pay attention to the regulation, and they have it the wrong way around. I'm not sure if it really breaks the USB specification or not, but it's bad design. Most of the time it's practical. Now the multimeter, let me remove it because we've seen that this works. I'll put it on the side, and let's have a look at journal control. And let's see what happens if we connect it. Oh, let me switch off my Wi-Fi. Down. So it only uses Ethernet. Up. Okay. Let's increase the font. So this is journal control, and it will tell, and it controls it shows the log of Linux system and all the other things. And whenever I connect USB, I'll just connect. So this is a USB key, a USB memory stick. Whenever I connect a USB memory stick, it should indicate that something is connected over USB. It also tells that this is a SATA device and mounted on it. And this will help us identify if something is recognized on USB whenever I connect the cable. So this is the original cable. Let's connect it. And there is absolutely nothing. So the cable might be broken. I don't expect it. It seems to be very robust. And it has even EMI favorite cores here to reduce the EMI. So it seems to be kind of a professional cable, but who knows? Maybe it broke internally. So let's try with another cable. Up here on my wall of cables, connected here, connected to USB. Nope, nothing. So I have no idea why a circuit on Earth or a spark on mains input could have caused this device to blow up. Although I do have an idea. Maybe there was a short through ground, not through here, because through mains, because this mains is probably input protected. But other devices were connected to the ground, and then there was a short to this ground, which is probably connected. Let's try if it's connected to Earth actually. So switch off multimeter, go back. So we see there's no USB. Let me just check with the multimeter. I'll not show it to you, so it's fast. Is it connected to Earth? Yes. This ground, let me show you on the multimeter. And we see that there's nothing on the journal control. Hub, multimeter, measure, this can be smaller. Current, okay. So here, Earth, and then we have the shield of the USB cable, which is connected, and whenever I touch it, it did work though. Huh? Why doesn't it anymore? Here. We see we have a resistance of 6 ohms. This means that this shield is connected to probably the ground, which is then connected to the Earth. Not sure if this is a good idea to make it. It is. I don't know what the specification says. I know on laptop it is floating because you have floating input. I don't know if you have to connect the shield here. It's probably because this shield is connected to the case, and the case is connected to Earth, because when you have exposed metal and mains input, you have to connect it to Earth. That's probably how they do it. But is the shield connected to ground? No. It doesn't seem so. Although not directly. 20 ohm. So the shield might be connected to ground, maybe through a capacitor, because there's still kind of a tiny connection. But we've seen no USB. So I'll put away the journal so you can watch the multimeter correctly, and I can watch the journal from my side. And the audio is still okay. That's probably the most important. So disconnect the inputs, and now we will open the device. As long as I'm here, mains input is fine. Earth isolated from line and neutral. No USB activity. Console powers up. Uses around, not for volts, but for watts. No USB activity. USB not detected. So this is exactly what he said that the problem is, and we've verified it. And that is the problem. And note your USB shield and ground are connected to Earth. And I think this is what the issue is. I think the short that happened on mains was probably across Earth. There was probably line or neutral which was connected, line which was connected across Earth, and they probably have it propagated to some path around here through the USB, through the computer, or I don't know exactly, and did something wrong to the USB device. But somehow it didn't do anything wrong to the rest of the device. That's just a guess. I don't know exactly what could have happened, else I would fix the device. So now we have to open the device. And there are tons of screws. So let's get this table, and this will help me organize the screws so I can know what screws goes where. I should have a pen here. This is not the permanent marker. This helps me. The screws. Back case. So here we'll put the screws which are on this side. It's probably easier for you to watch on the overhead because the view on this camera here is just not good enough. Screwdriver. Let's get it. This is it's a huge device. It's not common from electronics. Up, and this is actually a Phillips screw, while the screws are Torx. Posi drive. Do I have a Posi drive screwdriver? Nope, only Phillips. Good enough. Luckily the Posi drive screws are Phillips compatible. But not exactly the other way around. There are also screws next to the connectors, but I don't think we need to remove them. They're probably only to hold, we do need to remove them. They're not only to hold the connectors. Are they the same? I hope so. Let's see, else I'll have to open another box. No, they're not the same. They're longer. Line inputs. Oh, I heard a bracket which fell off. Not good. Probably this is, maybe their screws are enough to remove the cover. Let's remove all the screws. Not too many of them. Ah, come on. Who manufactures this? We have a third type of screws. Lamp. This is the lamp connector. We have first these small screws here for the case. Then for the line input, for the mains power input, we have longer screws. Now for the lamp, we have self-tapping screws. That's not a good design. I don't know who the mechanical engineer here was, but should have put a bit more attention for a high quality device. Apparently, I have no idea what the price of this is, but it was expensive enough that he wanted to send it to the manufacturer to get it fixed, so it should have cost a tiny bit. Not only lamp, but also DMX. Lamp plus DMX. Up. Two DMX outputs, probably has two universes. Surprised there's no Ethernet cable. No, there's none. It's just a DMX console for ArtNet or E131. And if you want to know more about DMX, I did a video explaining. I think it was called DMX Control DC Motor, where I explain what DMX is. So here we have 4 screws. That's bottom case. Bottom case. Up. Up. Oh, these screws are tiny. I don't remember if I have, for this camera, I don't remember if I have a fisheye. No, I don't think so. I have it for my other camera. Up. And last screw. For now, the last screw. I'm sure there will be plenty more screws inside. Up. Oh. So, I did not have to remove this, and I think I will immediately put back these screws. That's the power input. And we have a teeny tiny power supply with, what's the output? I think so. Earth is connected, that's correct. And then we have 2 outputs. I think they're the same. I would expect it to be 12 volts. What's written on the side? Let me first fix the screws for line inputs. These are the screws, and this way we don't lose them. 1, 2, but I needed to remove the other ones. Okay, So on the side here, you see it's a Meanwhile. Meanwhile is a quite good quality brand of transformers, but very common. Inputs, output 12 volts. We can check if it's 12 volts and how stable the 12 volts are. I think that's okay because we've seen it operates correctly, but I'll still measure the output. We are in volts. Can you still see the voltmeter? Yeah. Let's connect the input. Plug. Huge thing. Click. Cable is too short. My mains cable is too short. I have to get an extension. Although this mains cable is not short. Up. This is connected. This is the isolation. This is isolated, so I can do whatever I want. I won't get a shock normally. So this is ground. This is 12 volts. Oop. Oh, the plastic cover didn't hold so well. And we have 12.1 volts, so it's perfectly fine. The switch mode power supply seems to work well. And yeah, it's a lot easier to buy these ones because they're good. They're rated, and you don't have to rate the whole device again since you're using this rated device. Well, you still have to rate the device, but at least not for mains because you can say that's the one I'm using. And they're pretty standard. So this is the input. And we can remove it. So I can have a look because it takes too much space. And I can have a look at the board. Let's put this here. If I want to, this is a kind of a standard. This is kind of a standard power supply connector, and I think I have some of them, and it will allow me to provide my own power to it. Let's have a look. The power cable box. Plenty of this PC Molex connector. I don't know which Molex they're named, but here. Ta-da! I have the same cable. I think they just reused the cable. Even the colors are the same. So we will be able to provide our own power from a power supply, not using mains, and we can measure how much it uses. Let's put the box where I know that I need to put it back. Are the colors the same? I hope they use the same standards. Yes, yellow, yellow, black, black. And the two yellow and the two blacks are connected together. The two blacks are ground, the two yellows are 12 volts. And now, if I strip them off, we can connect them to the power supply. And I have to show you the output of the power supply. Data, project, multi-dashboards, DPS, stack, okay. Serial port not available. Let me connect, check. Now the power supply is connected digitally to the computer. And you can even see on the screen 12 volt output, a 4 volt output. No. Let's first prepare the cable. Let's remove this and have some space on the bench. Let's prepare the cable. They are quite thick. I'm not sure if this wire strip is good enough. Let's check. This one is good because it is kind of automatic. It kind of works. cut the wires to remove the heat shrink on it. I should put glasses on if I continue this way. Strip these cables. Up. Do I have to, so I don't need the isolation transformer anymore. Tack. Switch off. The buzzing is also gone. I don't need the normal mains power anymore. Switched off. Stream still works. This goes here. Do I have the crocodile clips? Yes. Red on the 2 yellow wires. This will be 12 volts. And black on the 2 black wires. They're probably even connected internally, so 1 wire should be enough. We can check it. Multimeter, continuity, multimeter probes. Yeah, these 2 are connected internally, these 2 are connected internally. So 1 wire should be enough. 1 of each wire should be enough because they're connected, but I can put both wires. If we connect the cable here, let's set the output to 12 volts, 700 milliamps. It says 4 watts, so 700 milliamps would be fine. Let's turn it over to see the activity. And if we switch it on, yes, we see 200 milliamps. And it switches on. Oh, this is kind of an animation, actually. Does this work? No. Probably this only works when it is connected. I don't know. But that seems to be fine. So, power off. Now we saved some space. Let's get the multimeter leads on the left. And you should remain to digital inputs. Oops, we're already losing connections. Okay. This is a huge board. They didn't clean, I don't know why here. For example, maybe this has been changed. Yeah, this has very probably been changed because these look clean. This doesn't look clean, so this fading unit has probably been changed. You see also marks here. We have some residues, flux residues. And we even have a budge wire. And I have no idea why there's a budge wire here. I even see other budge wires below here. For that I need to remove the screws. Let's call these central brackets. Central brackets. Up 1. 2. And 3 for central bracket. We also have screws on the side. And I think I will be, yeah. They're probably the same screws. So let's also call it central bracket. I need to remove the board because here, this USB connector right here, I need to see what's on the other side. Here we don't have any chips. Here we have chips, they are on the side. And like I've guessed, exactly like I guessed, this is on the top is on the wrong side because they mounted it on the PCB, which is right below it. So my guess was correct. Tack. Maybe we don't have to remove these screws. I don't know if we can open from the front. Let's first remove the screws, we'll see. Okay. I can remove just to remove the brackets, but it won't help me. Okay. So now I've just removed the brackets on the side, but it actually doesn't really help to get access to PCB. At least it's not as big. Wasn't necessary. So we need a way to remove this front plate, and for that we will have to remove these buttons. This goes here. So to remove the buttons we have screws right here. They seem to be a pain. Let's remove the connector, power connector. This way nothing happens. Let me get a flat screwdriver. Here. Flat screwdriver. And are these buttons individual or are they all the same? Some seem to be higher than others. Yeah, we'll put them like we see them. Normally we just turn a tiny bit, exactly. Just have to turn a tiny bit the screws. This releases the screws inside. And also a mark of not quality. You see this linear encoder trim pots. I don't know what exactly they are. They are not keyed. If you want good grip with screws, particularly with flat screws like this, you have keyed screws, so it holds better on it and it turns them better. So yeah, not the best quality. Or let's say they could be even better. Up. Second one. 6 more to go. Okay. Like this, exactly. Let me show you. Wait, this is up. Let's put it the same way. So here, two buttons here. For example, on this one. This is an encoder. Probably these are encoders too, but they're not the same one. I know that I recognize that this is an encoder, so every time you turn you have a quadrature signal output. This feels a bit nicer. And here you see the shaft is keyed. There's a flat side, so the screws holds tightly on there. But the problem is here that this screw is made out of plastic, so it is a bit more fragile than these things here. So if you knock too much on the buttons, you might break the screw, or if you turn the screw of the knob too tightly, you might also break the plastic. Just hold them tight enough so they hold, but not tight so they crack. Now on the left side, and I don't know why here they put kind of LED encoder, and here they put other types of encoder. Why don't they use the same parts? Might be a reason. And here you can see the other type of encoders. Maybe this is fine grain and this is coarse. Don't know. And on the left side, Did they use yet another? Yes, they use yet another encoder. This is black, this is gray. So I think it is yet another encoder. Yeah. I don't know what the difference between the encoders is. But they could have solidified the... Oh, even on the same side. Probably the same encoder. It's just that they have different batch. This is a different batch than this one, because this one is red, this one is gray, this one is black. That's weird. One knob left. Okay, last knob. Now we should be able to remove the cover. Oh, it's held by plenty of screws, these screws here, which we need to remove. Board screw. Board screw. So, hope they're all the same. Whoop. They have metal washers to reduce the slippage. I'm not sure this is really necessary, but it's not a bad thing. But they damage the they damage the gold plating. But hey, this is not something functional. So damaging the gold plating is not too bad. There's enough clearance on the side. You see that it is not packed. We see lots of electronics here because there are lots of traces, and here we don't see a lot of traces. And really someone put Kapton tape in here. Someone had a go. I don't know why they put Kapton tape on here and not on any other side of the PCB. Up. All the screws should be removed. Yeah, I cannot go higher with this camera. You'll have to live with it. Let's try to remove the cover. Did I forget a screw? Yep, I forgot one. Oh. That's a screw. I hope it is not held by any other. We have to remove the buttons also. This is easy. So that's all holding them back. Still you don't lose them. Okay. Tack, 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 tack. Tack. Tack, tack. I still have the feeling that I missed one screw. There's still something holding it back. Here you see in the middle one. It's hard for you to see. Get it? They're also held off by these three things. I have to recognize. How can I call bottom boards? Let's call them bottom board. bottom board. But not these two, but not the screws on the side, only these screws. So let me get up the wrench. Bottom screw 1, 2, and it's weird they marked with a permanent marker. They did put some crosses here. Clean it up too much. Let's mark it. Round mark. This will be also noted on the board there on the round mark. Now we can remove the cover. Okay. Cover removed. So here we have the USB. Let me do it the other way around. Now we need close inspection. And now you can see a bit better. There's even an LED. I don't know what the LED means. Probably that's weird. The LED just above the USB. But what you can see here, I think this is a input-output protection, a TVS. Here we have plus. That's normally minus, and that's the two data lines, if I am correct. Yeah, D plus, D minus. So we can check if this thing is working. It is really... See, there's plenty of flux residue. It doesn't look good. I don't think it did any damage, but it doesn't look good. Let's try to clean it off. With isopropyl alcohol. So this bottle is just IPA. Wondering what kind of microcontroller they're using. We'll have a look afterwards. Just let me clean off these contacts. I don't like this brush. I should have another one. This one. Finer brush. But normally they protect, but they don't blow. I'll have a look at it still. This one is really dirty. So, what kind of microcontroller are they using? Let's also clean up the microcontroller. This way we can better read. SMSC. Oh, that's not the microcontroller. That's the USB. That's a USB hub. I think you see here we have 4 ports, and I think when you connect to here, you connect to USB hub, which has 4 ports externally, and then something internally. And the microcontrollers are on a complete different side. Let's put this on the side here. And okay, this is an overkill from my point of view. They have 2 Xilinx, and when you see Xilinx, it's very probably FPGA XC95144. Let's check if it's an FPGA. Xilinx XC95144. Ah, CPLD. Okay, it's not completely an FPGA, it's just a CPLD, and what it allows to do is map all the inputs to other inputs, probably for this thing. This will probably program the two CPLDs, so it can read all the different inputs. Although I would use other devices than CPLDs, but at least it's not FPGA. And we see it is pretty old technology, because if you look at here how they let me get something to points. You see there's no solder mask between the pins, and this means that they weren't able to have very fine solder masks, so it means that the solder mask technology is a bit older. So the board is older. Is it written here? Ah, that's how the board is called. Southampton, UK. It's made in the UK. Okay. Magic Q PC Wing CH. I didn't even have a look at it. Yeah, that's the serial. It's second hand. It's not original. This battery should be dead by now. Although it is an I button. Wow. Oh, sorry. Let me show you. This here. That's an EEPROM, and this I button is very probably here to authenticate that this is a genuine board. Else I wouldn't know why they put I button on it. So they can probably program the serial, but for serial you generally have an EEPROM. You don't use an expensive I button. Maybe they also use it for the voltage it provides, although I don't know. I don't think it provides voltage. The I button has a battery inside, or kind of a condense capacitor, but it only provides data. So here there is an ID, and probably they have an I button for authentication. And this way they can be sure that the device is a genuine device, and I probably, my guess is that use this to avoid counterfeit devices, because they put lots of effort in the software and they don't want anyone to produce this board except themselves, although I don't know how much they sell it. It is a huge board, so it costs a tiny bit of pennies, but I think from the bill of material you would think around 100 euros, something like that. Looking at the buttons, the faders, these two things, the size of the board, say 100 euros. I don't know how expensive they sell it, but this is probably to avoid other people copying it. So this is the USB hub. So the USB hub seems dead. Next to the USB hub we have the clock. This is a crystal clock. We can see if it is resonating. And they did put protection. I'm pretty sure that these are protections. And Z very often stand for Zener diodes, like you see Z here. So these are input protections. Let's test if they still work. And we can have the diode check. Normally if we connect the data through the output, there should be, oh, okay, it beeps, meaning that data is passing through. So this was, which one is it? This is data plus or data minus, I never know. I think this is data plus, this is data minus. Yeah, the multimeter says it is bathing. This is very probably VCC, and this is ground. Yeah, ground. This is VCC, so it clamps. Oh, VCC. Come on. Wrong contact, or see the trace. Okay, VCC. And normally, if we now probe between I don't know if my multimeter has enough power. If we probe between these two, or this way, okay, the multimeter doesn't have enough power. But what happens is if you reverse the polarity, or if the data lines go above VCC, then this Zener diode clamps it down and avoids that further down on the line the microcontroller gets damaged because someone plugged something wrong here. They also, I don't know, they probably also are used for ESD protection and reverse protection. But here, you see 0.6 volts between ground and the data line. You see one of the diodes, and you should see the same result on the other one, 0.6. And same with VCC, we should see that one way or the other. They should be, maybe they at 5 volts. Yeah, they're probably above 5 or 3.3 volts because USB data lines are at 3.3 volts. The cost, which one costs? Something costs, match rejected. Something costs 2.6 euros. Yeah, the CPLDs probably, I don't know. Or maybe this one. So we can have a look. It's SMSC USB 2517. So let's put it here. You should be able to. I should be able to put you here. So this is the CPLD here, the Xilinx XC95. It is more like 10 euros. And let's have a look at the USB 2.5 something. I don't remember. USB 2517. And I'm pretty sure this is a USB hub. Resolving proxy, blah blah blah, embedded microcontroller, USB cables, here USB connector. Oh, it's only one word, it's not 2 words. Interface controller, I see, yes, it looks like this. Yes, microchip, this is the one, and this is USB hub, 7 ports. That's what I thought. And these are still available. Ooh, they're still available, and only 4 euros. Oh, you see, I don't know if you see a lot on the stream. That's good enough. Now we can test, and we can have the pinout though. Let me get the data sheets. The data sheet is there. We have, which part we have? It's in QFP or DFN? This is very tiny QFP. The leads are not very big, but this is QFP. Quad flat package. QFN, they are all QFN. Are there no QFP versions? QFN. Seem to be all the same though. That's the data sheet. Let me put it on a screen so I can watch when I debug it. And we can test if it gets inputs, voltage input and so on. Or I can try to share it with you. Here we have a look at the pinout. And on the pinout we can figure out which input, which pin is in it. is the voltage input, which one is ground, and so on. And we can see if the oscilloscope is actually running. Use the oscilloscope. The crystal is running. You're using the oscilloscope. So let's check if it gets power. Maybe this one is fried. Multimeter. Let's connect power to it. And click. Power is connected. We have loose wires. I have to switch the screen to show you the the multimeter. Up. Ah, the console is 2,000 euros. The 2,660 euros. Okay, so this, yeah. And this price point, I think it makes sense to put a one wire button to have an original one. But I think this is just, I don't know if this is authentication. The I button does authentication, or if it's just EEPROM. It's a DS 1963. We can also recognize the power because there are plenty of capacitors next to it, decoupling capacitors. Let me turn it around because I don't have access to it easily through the buttons. And yeah, you can still have a view on this device. So if I switch it on, let's just test it. Switch on 200 milliamperes. That's good. Means there's no short. And pin 1 is probably here. There's a marking here, and I only see a marking here, so this is probably pin 1. Right here is probably pin 1. Yep, that's pin 1. So it's exactly, this is exactly as we see it in the data sheet. You don't see it in the data sheet. I do see the data sheets. But there I see the data sheet. So plenty of pins. VGG. Where are the power pins? Let's just check on any of the capacitors. These are all the coupling capacitors. You should still see a voltage here. 3.3 volts. That's fine. The operating voltage is probably 3.3 volts. 1.8 volts. That's probably the internal core voltage. We see USB. I see USB DM and D plus there on the left side, and it makes sense. They're somewhere here. It makes sense because the traces go here, below, and probably in here. I'm not sure if they are inline protection resistors. Yeah, and my English, so also the microphone, it changes a bit the voice. So the voice you are used to is not exactly the same as what you're listening when I talk English. So that even makes it, even more disturbing. But I still don't see, VDD. There are plenty of VDD, VDD 3.3. Let me show you. Let's have another view so you can see my screen. Screen this way? Yeah. No, that wasn't this way. That shows you a bit for my screen. Bench all full screen. Like this. Up. And you can still see the remaining parts. Here we have VDDA, VDD8, 3.3 volts. Then again 3.3 volts. Somewhere on the left we had 1.8 volts. And here you can see on the data sheet 1.8 volts. Do have VSS somewhere. Normally VDD shouldn't be too far away from VSS, so you can put the bypass capacitors here. VDD again, VDD, This is PLL is for phase locked loop. This is to multiply the frequency of the crystal. Where are all the ground pins? These are all the pins. Normally there's a description on the pins. Right here, this is the USB data. USB power enable, plenty of things. USB hub, SDA, SDC. Ah, this is probably the data to configure the USB hub. So you connect it over I2C, and then you can say, please use that much power on this pin, enable or disable this port, and so on. But I want to figure out, so these are just all I/O, 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 where are all the power pins? Resets. We can check if this reset is high or low. If it's here, it's reset N, it means that it is active low. And we can check if this pin is low or high. But first, here, ground, VSS, there's only one slug. Ah! Okay, so that's why I didn't see the ground pins. Let's go back here. I didn't see the ground pins here because the ground is on the thermal pad in the center, the huge thermal things, this, what you see in gray. This is actually the common ground for everything. Now I get it. We can check the crystal if it's running. Because if the crystal, this tiny thing here, this is a quartz crystal oscillator, and if it is oscillating, it means that the so let's switch it to ground. It means that the IC is actually working, because the IC has to make it oscillate, and this will then respond to a certain frequency. Let's have a ground lead, and I need to show you the oscilloscope. Oscilloscope. So, get another script. C data projects multi. C capture. Okay. Continuously capturing. Now I have to, let me switch back to the bench. And I have to open this thing. Where's the picture from the oscilloscope? Dashboards here. Let's have it refresh, auto refresh every 2 seconds. And here you have a view on the oscilloscope. Let's check if we can see. So we connect ground, and then if we probe one of the 2 sides, we should see some excitation, but I have a bandwidth limit on 20, on the an input bandwidth limit. I need to disable it, because this is a bandwidth limit on 20 megahertz, and this crystal seems to be 24 megahertz. And I don't. Come on. Trigger. Okay, here I don't see any oscillating. Here I don't see any oscillation. So you see a tiny bit of things, but these are not oscillation. These are not the right oscillation. You should see a sine wave normally. This doesn't look at all like a sine wave. Okay. That looks more like noise than anything else. So this might be fried. That doesn't look like oscillation. Like a sine wave. I did remove the bandwidth limit. So my guess is that this chip is dead. The USB hub. Can we check if it is enumerating something? Because we tested the USB inputs. We could test also the USB outputs and see if it tries to enumerate. Although, does a USB hub? No, the USB hub does not enumerate by itself. I think it needs to have the USB host ask for the enumeration. Does this chip look damaged? Let me have a look. It doesn't look damaged. It doesn't draw too much energy. It's probably just not on. Let's have a look at the multimeter. With the multimeter, if the reset signal is there. Let's switch back to this. Now you see the multimeter. Let's check the reset pin. Where is the reset pin? The reset pin. Do I need Control F? Maybe the device hasn't been configured. The USB hub hasn't. I don't know. I think you have to only configure it once over I2C. I can also check the I2C lines afterwards. So these are all the ports for the downstream USB devices. Reset N. 1, 2, 3, 4, 5, 6. That's the 6 pin. 1, 2, 3, 4, 5, 6. Okay. 6th pin. So this will be. Is this ground? I don't know. This will be ground, and we'll have to check for the 6th pin on top somewhere. 1, 2, 3, 4. That's 6, and we have 3.3 volts. So the reset is not low. That means that the device is not held on the reset. That's good. It means that the host isn't holding it on the reset. 1, 2, 3, 4, 5, 6, 6. Yes, 3.3 volts. So it is not put on the reset because of the host. So if something happens, it's probably because of this chip. I'm really surprised that it doesn't oscillate. What is this device? There's a fuse. F1? Is this a fuse? F generally stands for fuse. It is kind of bumpy. FE. Does it look at? Yeah, it looks like FE and not F1. I have no idea what this thing is. What else can we check if this is the culprit? Let's connect again over USB just to figure out if cleaning or if moving parts around changed something. We can also test if it detects 3 volts on the USB lines. Okay, still nothing, no USB response. Normally if we connect, I think, because USB is differential, almost always, there's kind of exception for start and stop. One of the line is, okay, here one of the line is 1.14 and the other is 0.0. Okay, so this is not completely differential. Is it always this case? If we don't connect it, this is one line. Nope. This is where it would be useful to know how USB works. To detect when it is plugged in, one of the devices, one of the things should be pulled up. I think data plus should be pulled up to 3 volts. Isn't it this way? And this is how you can detect if there's a device on the cable, and then the host starts enumerating. Let me check on the sheets of any other device. So full screen here. No. I need any kind of other data sheets. That's not yet full screen. Let me give me the time to find a data sheet, and then I'll explain you what I mean with that it needs to be pulled up. Oh, actually, I can do it this way also. Full screen. So, if we have a look at just any kind of boards, I know I have a schematic somewhere here. Here, there's a schematic of this board, and if you have a look at the USB, EEPROM flash, Wi-Fi, where's USB? Where's the USB connection? Here, USB. D+, you see that D+ is connected to 1.3 volts using 1.5K. I think the 1.5K is just there to indicate that this is a full speed device and not a high speed device, but I'm not sure exactly. But in any case, this is definitely not pulled up. Let me check again. So this is, which one is D+, which one is D-? Which one is ground? I think this is plus, this is ground. Let me check. Yeah, this is ground. We can check it. Well, if we switch off and then go to continuity mode, and if we connect the shield to here, we see, yeah, this is ground. This is V-bus, so 5 volts. So it means that this is D+. Yeah. No, D-. No, D+. D+ is on the ground side. You have to look at the... I have cheat sheets for that, but the cheat sheets are just the same as here. USB, somewhere there are, here. You see that on the same ground as minus is D+, and D+ needs to be pulled up to 1.5 to 3.3 volts. So if here it is not plugged, it is not pulled up to 3.3 volts, it means that, yep, no, that's kilo ohm. Up. Now I have to power this up. It is powered up. If this is not at 3.3 volts, it is not. You can't barely see, but you can see it. It's 0.11 volts. So the data plus is not pulled high, and because the data plus is not pulled high, the host is not able to detect that the device has been connected, and it will not start the enumeration. So it may be just a resistor the pull-up resistor which has been damaged. Ah, and I think this is the pull-up resistor. Here on this side, this is probably the thing which pulls it up, because you very often, to reset the USB device, you have to pull the, to do a USB disconnect, or to do a USB reset on the D plus line, you disconnect the 1.5 volts and then you reconnect it. When you disconnect it, when you disconnect the 1.5 volts from the 1.5 kilo ohm resistor to 3.3 volt, it means that nothing is connected, so the host will detect it as a disconnect from the USB, and then you just re-enable the switch. And I think this is what's here. And if we look, oh, it's tiny. This is the secret. I do have a macro lens on this device. This is very probably a transistor, yeah, TR1, something like transistor. Ah, and you see 154, or is the resistor 154? There's a marking on it, and the marking is 691. That's 680 ohm. That's not the right one. How do you tell if it's USB full speed or USB low speed? There's something with that. USB 2. Let's see. Pull up. I don't want to have a look at the data sheet of USB. USB pull up D plus. Let's have a look. USB in a nutshell. I think this is a good start actually in the beginning. Here, electrical. This is what I meant. To ensure, although in full speed devices the virtual is transmitted over to with a 50 kilo ohms resistor. This is for low and full speed devices. Is this what we also had here? That's 1.5K. Ah. And with a pull to ground and D minus on the, wait. There's something wrong here. This pulls it up to 3.3 volts. Speed identification, yeah. Ah, here, speed identification, full speed device. Full speed means 11 megabits per second. This is what we have on this development board. This is a full speed device. We see that the full speed device needs to have a 1.5 on 3.3 volts. And on, actually here on the low speed device, 1.5 on 3.3 volt. Okay, so on high speed mode there is no pull-up. Speed indication. The high speed indication will start by connecting as a full speed device. Once it does, it will do a high speed chirp during reset. But okay, it's not, I didn't know about that. I didn't do a lot of high speed. I only work with devices which do full speed. And high speed is 280 megabits per second. Full speed is 11 megabits per second. So it starts being a high-speed device, and then it switches, full-speed device, and then it switches to high-speed using a chirp. But we need to find somewhere a 1.5 kilo ohm resistor. Maybe it is embedded in this thing. I don't think so. Is there a design recommendation this device to tell that you need to have a pull-up resistor, an external pull-up resistor? Pin description. So on the left, do we see any device recommendation, design recommendation? Pull contains internal pull-up resistor to 3.3 volts. That's not what we want. Resets, that's okay. Here. Okay, let's VBus detect. Pull-up resistor. External pull-up resistor, that's on the data line. So SDA is the data line, SCK is the clock line. This is for the I2C communication. I2C programming. What we can also check if during boot up it does check the I2C lines. I don't know if this is EEPROM. So wait, I've seen quickly here I2C EEPROM slave address. Okay, so it means that this device kind of is recognized as an I2C EEPROM by the microcontroller, meaning the microcontroller only has to configure it once, because the data is stored in the EEPROM and then the USB hub is configured. It can still reconnect to reprogram it, but I don't think we will see any activity on this hub, because you generally do it once you flash the first device and never afterwards. Fully integrated USB termination, pull up and down resistor. Means that we don't need to have USB termination. Okay, USB termination is the 22 ohm on the lines, and then pull up and pull down resistors. So it means it doesn't need any external pull up, pull down. But we still see that if I connect, yep. If I connect here to here, we should be at 3.3 volts. We are not, yeah, we should be at 3.3 volts. We are not at 3.3 volts. This is why the host is not starting to enumerate the device. Now I have to figure out why is this not pulled up to 3.3 volts. Okay, we won't find, it would be nice to have an external resistor, something, these are resistors, as you see the marking is marked R, but apparently this chip has embedded pull up and pull down resistors, so we don't see them externally. But we can check on the lines of the device. Here, E plus, this one, 1, 2, 3, 4, 5, 6 from the bottom left corner. Here they should be 5.5 volts. 1, 2, 3, 4, 5, 6, still not. So even on the output of the chip there's not 1, 2. No, there is no 3.3 volts here. Okay, this is why it is not recognized over USB. Is this chip dead, or does it just need to be reconfigured? We have to connect to the I2C lines. What are these two pins? 1, 2, 3, 4, 5 and 6 from the top left. 1, 2, 3, 4, 5 and 6. This is the USB output 6, so this is probably, I don't know, this probably goes to the other microcontroller. So here we have, so these are the CPLDs to connect all the pins and to interface all the pins. This is the main microcontroller. It's Silicon Labs C8051, so it means it's an 8051 core, F022. It's not expensive, one of the cheaper ones, but apparently and probably this one also provides, it has USB integrated, and this is where where is the camera? This is probably where these two lines go. What you see here, these two lines, this is for port 6, and they probably go all the way to the other chip. Check again. Yeah, it's not 3.3 volts. What if we pull it up ourselves to 3.3 volts using a 1.5K? It is cheating, but why not? Let's try to find out. Let's have a through-hole resistor. $1.5K. Do I have a value like this? Nope, not here. Generally, when you do USB, you do it over SMD, so you have tiny pop-outs. But now I need kind of a through-hole resistor. I do have through-hole resistor sets. Resistor through-hole up, up. Let's switch to the top camera. Bench. So my resistor box, and let's find 1.5 kilo ohm. I hope I have one. 2 kilo ohm. 1 kilo ohm. Yeah, nice. I don't. Not in here. I know I have another set. Resistors. Here. Let's put this back. Set of resistors. Oh, I can leave this actually here. Do I have something? 1.5K, 1K, 2K. No, I don't. 2K, 2. Come on. This is a very standard resistor. I probably only have it as SMD. So, not the through-hole part. Let's find out if we have it as SMD. I know I have it as SMD, that's for sure. Capacitors, power, MCU, inductors, here resistors. Let's have a large one. $2012. Yeah, yeah, a sample book of SMD resistors. Let's see if we have 1.5K. 1K. I think I will have to cheat in the end. I don't have 1.5K here. On the other side, maybe 1K, 1.5K. This is 0603 Imperial 1608 in metric. I don't have a lot of them, but they're here to be used. 4. I only have 4 remainings, but let's use them. Here we are cheating, really. The USB hub should be putting this 1.5K on the data plus line, and we are forcing the device with 1.5K. Hub. So let's switch to power off. Let's switch up. Let's switch to iron on. And here, where is it? Here, this is the one we will we want a resistor. We want to solder on the device. I'm not sure if this even works or if it will force enumeration. Let's check it. So okay, this one side is working. This is soldered on, and now we need to solder 3.3 volts, which we can disconnect. Let's switch this back on and find where we have 3.3 volts. We have it. We know we have it on these chips. Do we have it somewhere here? This is input VBus, so this is not where we will find it. Do we have to have it against one of these capacitors? That's ground. That's nothing. Okay, this one has no voltage. Why don't you? That's 5 volts, so this is for the downstream. This is nothing. Come on, I need 3.3 volts somewhere. Five volts. Oh. 5 volts. This is the pull-up resistor for this transistor. I don't know what this transistor... this transistor is used for this LED. Here we have the 5 volts from the LED going in. Then it goes through this resistor, and this resistor connects into ground then. This is just to control this LED. And this is the pull-up resistor, so by default, or pull down, I don't know, so by default it doesn't switch on the LED. It switches it off. As this 3.3 volts, this is ground, and this side is nothing. This is weird. That's not normal that both sides there's nothing. Should be power. Let's remove the soldering iron for now before I burn myself. I think this isn't ground. We know that the shield is ground. We should be able to measure. 3.3 volts. Here we have 3.3 volts, but it is far away. Do we want to go so far just to collect 3.3 volts? And they did good job. Here we have a PTC fuse. For every port, it means that if the devices connect here drain too much current, this fuse will trigger. Normally it's 500 milliamps, and it will disconnect back. So they did good design here. And did put, okay, 3.3 volt, we also have it here. And we also have it here. So we can take it from one of these devices up. How do we want to do it? I want kind of a cable or a switch, so I can disconnect the 3.3 volts. To have an inline resistor, inline cable. Or should I just connect it by hand? Up. One cable. That's good enough. And then we will have a 2-pin header. I don't have any of these anymore. cables ahead, and we need a jumper. So we can disconnect it if we need to. Now let's solder everything we need. Oh, let's prepare this thing up. Solder. This header is quite old. I need, because you can see by solder this. Yeah, this header is quite old. You can see it. Thanks to how the solder reacts to it. If it forms bubbles, that the contacts are kind of oxidized or old, and it should flow around it like this. A bit of solder. My leads are old. So I need to tin the leads which are already tinned, just because the solder is old. Yeah, seems like this. Up, one lead connected. Now the one, the tiny one, I do have here. This is normally a plier for fiber cables, but it is really nice for this tiny wire, which is an AVG 30, I think. Teeny tiny wire. Up. Doesn't look nice. Solder is old. See that the solder is old because it makes, when you move the soldering iron, it makes kind of spikes like this. This is not a nice looking spike. Did I put, yeah. Up. So this is ready. Let's switch off the power supply to the board while we are soldering on it. Up. Let's switch this on. Let's solder it on this one. Here we have 3.3 volts. Up. Ooh, it's a lot of stress. And here we connect, we solder to the other side, to this tiny resistor here. Tack. Now it solders, now we have a pull-up. If we put this up, if we put this jumper here, we have a pull-up to 3.3 volts. Let's check if it works. Switch on the power, it still only draws 200 milliamps. Means that nothing is shorted or drains too much. And if we check now, we're at 1 volt. So something is pulling this line down. Here, 3.3 volts. Here, 1 volt. Something is pulling this D plus down. And it can only be this chip. Okay, let's check the connection. So it's switched off. Let's check if we connected on the right way. So continuity mode. On continuity mode, we tested the pins. So we need to pin 1, 2, 3, 4, 5, 6. D plus should be on pin 6 and D minus on pin 7. 1, 2, 3, 4, 5, 6. It's not connected. At least not. Ah, sorry. Wrong contact. 6, yes, it is connected directly. Less than 1 ohm. And D plus. Oh. Wait. What the hell? D plus and D minus are interconnected? Okay, no, it was just me. 1, 2, 3, 4, 5, 6. And on top, that's D minus. 7. It is also connected directly. Okay, so there, the pins are connected on the IC. The IC is pulling this line low. Is this IC wrongly configured? You shouldn't put this line low. Go to volts. USB, we're still at 1 volt. It should be 3 volt because it's pulled up if there wouldn't be any issue. Is this one pulling it low? I don't think so. No, it can't. And it wouldn't be 1 volt. Maybe this diode, who protected, has been burned. How do you test inner diodes? If they work okay, you have to test on both sides. So switch off, go to diode test mode, diode test, diode test. This is ground, and if we put it on ground here, and on this volt 0.6 volts, that's the one diode, 0.6 volt, it's the other diode, and on the reverse it shouldn't pass any voltage. So if we do it this way, oh, is this normal? Also 0.6 volts? That's weird. Okay, let's test it here. 0.7, 0.7. I have to look at the data sheet again from this thing. 0.6. 0.6. Okay, I don't know how this works. I do have a data sheet for them because I've used them. Let me find the data sheets. Data. Display. Diode Schottky. TVS USB CL, this one. Where can I put this? Oh. Let's switch to full screen. Now we're on full screen. And here, very low capacity. This is really for ESD protection. And we see that ground, wait. If we check the line here, so it is pass through on ground. If we check it one way, So here we should measure 0.6, that's okay. But if we put the ground lead here and the plus here, we shouldn't measure, we should only measure the Zener diode here, but the Zener diode should be at 5 volts. So these are normal diodes, these are the Zener diodes. And the Zener diode reverse should be, where is it, leakage currents, volts, capacitance, clamping voltage, 12, is this? Forward voltage, 1.6 volts, I think the forward voltage is from these diodes here, and we measure only 0.6 because there's no load. The device was not on. Surge protection, yeah. So this explains what the USB protection does. So yeah, normally, yeah, if I connect one of these two lines to ground, so if I connect ground here and this here, we should see 1.6 volts, 1.1, or in our case 0.7, probably another one. But we shouldn't be able to see any voltage if I connect ground here and plus here, the leads. It would indicate that this is broken, wouldn't it? But I wonder, so I think these are the devices. This is clearly ground because there's a via, and if we connect it here, this is ground. If we connect it to this line, 0.6, 0.6, this is really weird. .6. I think I have some of these parts, so we can test the parts separately. MOSFET diode, here my diode book. I have to switch back to full screen. Oh, you can see it partially. Yeah. Bench. This book here. Diode MOSFET LEDs. In here I should have these USB protection devices. Here, USB LC6. These are the same. Oh, I broke the cable, but luckily I didn't break this thing. But we know that this didn't work, so let's remove it for now. So we won't do any damage on the board accidentally like I just did. Let's take one of these pieces and measure if we see if we find the same thing, because I would be okay that it misbehaved here because this should be broken. Why should it misbehave here? And we see the same behavior. So if we connect, I don't know which pin is which, what is 0, I don't care. Because if I find it off one way, it shouldn't be on the other way. So let's try between here and here. Damn it. If I put ground here, okay, not this way. Okay, here I don't see any voltage drop. Come on. 0.8 volts. This is the internal voltage So this is means that this is ground. Here we should see, at least on one of both sides, we should see 0.6 volts. Ah, here, 0.8 volts. That's more like it. And now if I reverse, if I do this way, we should see nothing. Yeah, we see nothing. This is blocking correctly. Ah, you don't see anything on the camera, sorry. We can put, let me put this device so you can, on a socket, so you can see what I'm doing. I'm better than this teeny tiny board. SOT 26, 23 I think. I should have 20 boards, 23 boards. I don't think this is psych. Does it fit on here? SOP, SSOP. I don't think this would fit in on there. Would it? Check. Could fit on there. It's not the perfect pitch, but it could fit. SSOP. I don't have any sub 23. Well, we'll do it this way. And I need to mark which is pin 1. What does the datasheet say? There is a dots. Can I see the dots on this thing? I don't see how they see it from the bottom. How does the CNC know? Maybe the CNC knows, the pick and place machine knows it. Yeah, there's a tiny dot. It's teeny tiny. Can I show you on camera? Let me try to show you. Oh, didn't expect the macro length to work that well. So, if we have a look at this piece, right here, you see there's a tiny dot on this corner. And this is pin 1. Now let's solder the device. So, to solder it, I put first solder on the pads, on one pad actually, and only on one. Okay, so I solder on one pad, take the tweezers, uphold it, put it in place, like this, drag the solder on this one pad so it connects to it. And now it should hold correctly. Let me check if this is really pin 1. Yes, it is. But the camera, it's hard to see. And now we can solder the other pins. The other side now. Okay. So this is easier for me to identify which is pin 1. Here we have, this is marked, this is pin 1. This is the pin 1 here. So if we look at the data sheet again, between pin 2 and pin 1, we should have 0. If we do it this way, we should have 0.8 volt or something like this, 0.8. And if we do it in reverse, we should have nothing. And we have nothing. So this is behaving as I expected. This is not behaving as I expected. Here we have ground. So if we connect the plus lead to ground, and then this one to I/O, 0.6 volts. But if I connect it the other way around, we should have nothing. And we still have 0.6 volts. So somehow, I think this part is damaged. And probably these are too, because they behave the same way. And let me just check which one is pin 1 here. Pin 1 is always bottom right. Here. Pin 1 is always this corner. So if this should be ground. The pinout should be the same with almost all of them. Let me check what is written on top of it. UL26, something like that. Up. Can you also see it? No. Yeah, the exposure with the camera is not great. It's written UL2. It is a 6 or a B, and it's a 6. And we see that on the top marking here, it's also UL26. So these are the same devices. These are really the the TVS diode, so the ESD protection and all kind of protections. And so if I connect, so this is ground, and if I connect here, we should have 0.8 volts, yeah, something like that. We should have one diode, but if I connect it this way, we should have nothing, and we still have 0.8. It really means that this thing is damaged. If I do it here, this is pin 1. If I connect it this way, I have nothing. If I connect it this way, I have 0.8 volts. And I don't see any part of the external device being responsible for, I don't know how other devices, because the board is not powered now, so nothing should interfere with our measurements. So what we will do is we will remove this chip. We will replace it with one of ours. Then we will measure if the behavior is the same. Or we can measure if this device is broken, and if this device is broken, we can replace it and still measure once it's in place. But once it is removed, we can check if it is broken or not. I will do it with solder. Normally, surface mount devices, I desolder them with a hot air iron, but here we have plastic next to it, and I don't want the plastic to melt. So we will use low, where is this? There's this one, here, bismuth. This is bismuth solder, so it is low temperature, but more important than low temperature is that it is a liquid for a long time. I think it's called eutectic region is quite high, and that gives us time to act and desolder. So now let's desolder this chip. So we put solder on all the pads, one side, on the other side, and yep, now it's removed. Here's the device. So let's test this if this is broken. Let's put, oh, we don't see anything. this part. Where is pin 1? Oh, damn it. I did find pin 1. I don't anymore. This is pin 1. Now we can check if it is still measuring faulty. And if yes, we know we have at least one culprit. So, if we connect the plus probe to ground, then this one I can't hold it down. Damn it. I won't do it under the camera. I don't see anything. Which one is pin 1? This is pin 1. I'm doing it off camera. Yeah. This is so. If I connect this one here and this one here, we should see 0.8 volts. I cannot hold it. We don't see 0.8 volts. We see nothing anymore. Did I completely burn it by desoldering it? No, 1.8, 1.14. It's okay, we see this way around. If we check the other way around, we should see nothing. And we see 1.8 volts. So this device is broken. Yeah, 1.8 volts. We should see nothing. Let's replace it. So, to replace this resistor, this part, we need to clean the pad with preferably solder wick. Let's do it correctly. And I expect the other ones to be broken also. What if we measure now? We should measure nothing between the signals. 0.8. What? Oh, they're cheating. I don't know if this is how it is supposed to be. I have to clean. Let me clean the pad so you can see correctly. Well, it is still working, but I don't know how this is how it is intended. Yeah. Tiny bit of flux here, tiny bit of flux here. Up. Where is my side cutter? Side cutter, side cutter. Here. Side cutter. I might still use you. Let's clean the pad. Let's see what I'm doing. Now I'm cleaning the pads. Then I can show you what I found. We can remove this resistor. Yeah, resistor removed. Up. So, what do I mean by cheating? Here, you see they put a line between these two pads. So, the diode in this package, which is still protected, which will still protect it. But if the diode is dead, or if this part is not populated, then the USB still works. But I don't know if this is really a recommended way to do this. I didn't know about it. I never thought about doing it this way, because really, if you put the USB protection, then it will still be protected, and you're not cheating, because in the package these two pins are also interconnected. And if you don't put it, then you don't have any protection, but you can still USB. It is not a stupid idea. It is a good idea. And we see the mark 1, pin 1 mark, which is here normally. So now we have to clean the pad. Once we've cleaned from solder, we have to clean the flux residue. From the solder pad, just using alcohol, and then it looks correct. The problem is that because it is now interconnected, I cannot test it correctly. And I don't know. So if I touch, this is ground that we figured out. If we, for example, if I connect it here, 0 to the shield or to any other ground, what is ground? This is ground, for example. We see 0 volts. This is ground. This is also this pad. If I touch it here, it still says 0.7 volts. That's, if there would be a diode, that would be the right voltage. Here we don't have any diode anymore. It means that the package here, this chip here, also has an diode protection, input diode protection. The problem now is that if we do it the other way around, this way and here, we should see nothing. And we still see 0.7 volts. Oh, should we see nothing? I don't know if we should see nothing. At least, this is so. The culprit in this case was not this chip, or not only this chip. This chip is also broken, because if I measure here and here, we have 1.8 volts. And if I measure 1.1 volts, if I measure between here and here, we also have 1.1 volts. We should have nothing. So this is clearly damaged. But I'm almost confident that this chip is also damaged. We've tested, let's go directly to the chip. And there's, I don't know what this thing is. Is it connected? So there's a fuse here, maybe this fuse, this is just a fuse, it should do nothing. It should only be inline. And we checked that the pads go directly through it, so the fuse, even if it were broken, it doesn't connect the two USB lines. So we did it, and this is, if we have pin 6, 1, 2, 3, 1, 2, 3, 4, 5, 6. This is D plus, and the next one is D minus. So these are connected correctly. Yeah, this is a fuse. Yeah, this is a fuse for somehow 2 lines. This is probably an input protection fuse. Is this one going here? Yeah, I didn't know this part. This input protection fuse. Yep. The 2 data lines of USB go also through here and then in here. Is this fuse maybe damaged? No, this is in line. It wouldn't, if we test between both pins. Why do have 1.1 volt between both pins? Is this usual for USB hubs to have 1.1 volts between both pins? I don't know USB hub well enough for that. I have to take apart another USB hub. We know this blew up. We don't know if this also blew up. This is the probably next culprit, if not the fuse. Maybe the fuse blew up. Let me get a USB hub. I can check. I can take apart. So, I just got an ESD discharge. So, cheapo USB hub. Let's open it and let's check what's inside. And let's see how this behaves. But this is a really had to sneeze. This is a really crappy one. I don't expect to have any kind of protection inside like this. Oh, this has TVS protection, so this has lots of protection. This has fuse protection on the output, these things. Here we have TVS protection on the data lines. We also have a fuse inside, so it is well designed, at least on the USB side. And I don't expect this one to be that well designed, but we'll find out. We'll find out. So let's open it. There are no screws here, are they? Are they? No. Should only be clips. What? Okay. Up. Let's have a look at inside. Here, we already see vast difference. This is a single chip solution. See, here under this blob of epoxy, there is one chip directly soldered on the board, called chip on board. We also have only one-sided PCB. See, on this side we have no traces, because one-sided PCB costs a tiny bit, a couple of cents less. And how did I recognize it? You see these links here? This is because they weren't able to fit all the traces on one side. So they have to add copper traces, like wires, like the bodge wires, on top of that. And you see them here, here, here. What you often do is you connect ground or power with it. These are a tiny bit resistive. And yeah, when the design is not perfect and not completely one layer, you have these kinds of wires which you have to connect. Yeah, completely different quality, right? But let's now measure what's interesting for us. Let's measure if, when it is not powered, between data plus and data minus, this is the input, we have a voltage, a diode. 1.4 volts on one side, but nothing on the other. Is this the same here? 1.2, 1.2. If we do diode test, I have no idea if this is intended or not. Here 1.4, but if we do it the reverse, we have nothing. Let's have a look at here on the downstream. Nothing on this side, nothing on this side. It's really just on the input. 1.2, 1.2. 1.4, nothing. Okay. We even have optocouplers, optic out. What can we do? Let's have a look at the data sheets. If the data sheet tells something. So it's not the data sheet. Let's go to screen. Let me switch off the soldering iron. This can take a couple of minutes. I again got shocked. Let me wash my hands because I touched solder and I want to remove the lead. Okay, my hands are clean and the lead has been removed. Now, let's check on the data sheets. If we find something telling the difference between the pins, USB data pins, that's the detection. Okay, these are the downstream ports. This is the upstream port. LED indicator, LED. I can try to talk ITC to see if it still reacts and if it is configured correctly. EEPROM interface behavior. Configuration select. Okay, this is how you configure if it's using SMBus or EEPROM. SMBus is a derivative of EEPROM. It is very similar. LED functionalities. Okay. These are the LEDs. 7-port hub, configuration options, EEPROM. Here, register address, PID, PID. So this is where in the EEPROM you can configure the device. If we see that the SMBus power on reset value, internal default ROM. So these are the default values. What are the power on reset values? Why is it different than the default ROM values here? SMBus and EEPROM. POR stands on power on reset, right? I don't know. These are all the bits for the register, so we could try to dump it, the string, blah blah, tons of things. Where are DC parameters? Here, maximum rating. So this is the rating for the inputs. Ah, also the crystal, exactly. We didn't see any activity on the crystal. Maybe it goes to sleep. That could be the case. Is it always running? I don't know if it's always running. Maybe sometimes it goes to sleep and the oscillator is not running. This is why we don't see it on the oscilloscope. We should see it at some point, at least during boot. So we can try during boot to see if the oscillator are running. Pin capacitance, pin characteristics. Yeah. Yeah, 24 megahertz. This is what we've seen on the crystal. We've seen the 24 number. Okay, we have no indication. So, there are two things we can test. One is check if the oscillator, the oscillator are running when we power it up. Let's check when the oscilloscope here, this is still running. So let's check when we power it up. Is it running at some point or another? If it's not running at all, it means it is not going up and it might be broken. So this USB hub, this shitty USB hub, which we cannot use as reference, removed. I actually don't use them as USB hubs, I use them as power hubs only, because as USB hubs they're really not good. So here let's tag auto. Now if I power it on, is this connected correctly? Oh, now we see some activity and then it goes to sleep. Okay, let's do it again. Power it on. And there we see some activity. This is nice. And somehow it wasn't able to measure. The oscilloscope wasn't able to measure the frequency. This looks a lot nicer. 1 volt peak to peak. This looks like an oscillation. Let's power it on again. Yes. This looks like a clean oscillation. Now we want to measure the frequency. So horizontal frequency 24 megahertz. I don't know why it wasn't able to measure on the top right corner. You should also see the T. It says under 15 hertz. It should also tell that this is 24 megahertz. This tells us that the USB hub is able to boot up. Yes. Yeah, 24 megahertz. It is able to boot up. If we check the other pin, it should. Do we also see something when we check on the other pin? I don't know. Yes. Also 24 megahertz, a bit more, but measurement errors, and plus it needs to tune in. And then it goes to sleep. And probably it waits. So we know the chip is not completely dead. Maybe just the inputs are dead. Let's connect this and see if this works. Oh! Oh, no, that's something different. No, is it? No, chances. Can you see what I see on the right? It detected it over USB. It works. And without protection. So the input protection blew. LS USB. Oh, I have too many devices. LS USB. Watch LS USB minus T. No, not minus F. Minus T. Okay, I don't read it. I have too many devices. Here, 1475. 147. This is below. 1475. This. And we see this hub. This is the hub with 7 ports. If we disconnect it, this should disappear. Okay, it's not exactly this one, but just below. When we connect it, this one, this is the hub, and then on the hub we have the FTDI driver. And, oh, they're using FTDI. Ah, Silicon Labs, this is also the one which drew the FTDI. Is it? No. The FTDI is done by, I don't remember. But yeah, USB works. USB works. So I just need to solder, yes, woohoo, as you said, woohoo. It seems to work. I don't have any software to test it though. So let's disconnect it and let's solder a protection resistor and let's replace it. So let's disconnect this. Everything is disconnected from power. Let's switch back to the screen so we can solder a protection resistor. So in my booklets, let's use another one. Where are they? Yeah, these ones. Can I put this one here to know that this is a USB? Oh, this was for demonstration. I can throw it away also. Here, let's peel off this thing. Let's get this one. Up. Switch on the soldering iron. Switched on. Now we'll do the same technique to solder. I need to figure out which way is pin 1. Pin 1. Should be a tiny dot. I think this is the tiny dot. Let's check. Oh, it's on the U. Okay, this is pin 1. Oh, it's so tiny. I need. Where's the lamp? The flashlight? Where is my flashlight? I lost it. Luckily, I have other flashlights. Yeah, with the flashlight, it is a lot for you, not because it is overexposed, but for me, it's a lot easier to see pin 1, and it goes this way. Oh, actually, I could use the camera. The camera seems to be able to use pin 1. So we need to solder this right here. So soldering iron should be warm. Let's put the first blob of solder. A tiny blob of solder. it's not cleanly done. The keyboard is on the way. And the camera is on the way. But I think, does it look nice? Let me have check. Yeah, it's not perfectly centered. Let me just do it with my head in front of it instead of the camera, so I can have a better look. It's a lot easier, at least for pin 1. For the other ones, you're allowed to watch. So, pin 2. Actually, you're not allowed to watch. No. Let me do it this way, so at least you have a feeling what I'm doing. And I need to watch it myself for this. The solder doesn't stick well. When the solder doesn't stick, you put some lubricants. And then it slides in really easily. That's all the magic there is to SMD soldering. Plenty of lube. Okay, so the replacement is there, but if you put lube, you have to clean it. So, isopropanol and looks clean. It is not completely, so this textile is baby wipe, which is dried off, and it's good because it absorbs quite well. Sadly, it is not completely lint free. Let me check if it looks correct. There's one pin which doesn't look correct. This one, I'm not happy with this one. Let's check with the contacts. Beep. If it makes beep, it's okay. Yeah, it's okay. So let's clean again. Clean it. Yep. Have a look how it looks like. This looks okay. Not perfect, but it will hold. So here we see I've put too much solder. There's too much. There should be just a tiny bit of solder, but that's fine. It holds well. This chip goes here. Now, if I switch it on, the power on, it draws 200. Let's switch it on. This here, no dreads. Switch it on. It only draws. Oh, it doesn't. Connection lost. Why doesn't it show it to you? Press N key to stop. Stopping capture. Why don't you show anything anymore? Okay, now it shows that it draws output currents, output voltage 12 volts. This is not precise enough. I have to change that. It draws 200 milliamps. Yeah, this is not precise enough. Okay, I need to fix this, but this will be for the next time. So now let's see if the USB gets connected and if it finds it. Full screen. This up. We remove this. Let's zoom in here. And normally, if we find something on port, was it on port 5? I don't know. We'll see. If it connects, if USB is detected, then it works. Tack. Ta-da! 7.5 FTDI. And here we see that FTDI transits WinPC. That's done. This is fixed. I have no software to test it though, but at least it is generating over USB. I have absolutely no software to test if everything else works. This will be up to the owner of this device. I don't want to install any Windows and any software to test if everything works. USB is recognized. I don't know. I want to test if this acts as a hub. If I connect a USB stick, does it work? Yes. Yes, the USB works. And it detected the USB storage, so even the USB hub works, so you can use this device as USB hub. And it was really this thing which blew up, and this is what it was meant to do, blow up when something is broken. So now I need to put everything back together, and the job is done. Up, so switch off power. That's probably now very boring for you, but it is important for me that when I put everything back together, it still works in the end. So let's remove everything which we don't need right here, so I have a bit of place to work on the thing. We just moved it to the side, and I will put it where it belongs to, at the complete end of stream. Up, this goes here, this goes here, this goes here, that goes here, that goes in the bin. Oscilloscope probe on the oscilloscope. Let me switch back the camera. Up. That goes here, that goes here, that goes there, that goes here. I need this to put all the things together. This goes here. Oscilloscope. Here's my flashlight. At least I found it now. Up, up. Trash, and this goes here. Okay, most of the things have been removed, and I have enough space to work. So we can switch off the oscilloscope because it's noisy. Up. Let's switch off the plug. Now we need to put up the top. This goes here. There were at least 3 screws, but there was more. These 3 things go, don't they? Okay, they do. Just it wasn't holding correctly. Camera, these zoom out and try to have a view on what I do. Now we go backwards and screw everything back together. Up. Not too strong, I don't want to break the pad, it just has to hold together. Now these screws, plenty of them. Up. Damn it. screws are remaining. Yep. Let's also clean these things up. I don't know who changed this, but we will also clean these things once I've put all the screws on the back side. So many screws. I'm still wondering what this botch wire is for. Have 2 screws remaining. Is it right? Yes, that's right. At least we didn't lose any screws yet. The screws are magnetic. I don't know. Let's try to magnetize the screwdriver a tiny bit. No, they're not magnetic. And here. Up. This way. Now we can put back all the buttons. Do we put them back in the end? Let's put back the side things. Brackets. So brackets. Oh, I didn't pay attention. I think it goes this way. Duck. This goes here. Cling, cling. Yeah. Clack, duck. Yes, somehow, not completely. Here. So the screws for these things. Duck one. This one wasn't screwed enough. Let me first at least put screws so it holds together. Can still. Why did they put several holes for different models, for different board models? Because here we didn't have any screws. It seems that different models, they have screws on other places. Oh, now they're in place. Now I can screw them tightly. Up, this is in place. 3 screws remaining. One. Two. And that's the wrong screwdriver. This screwdriver fits better. Okay. Let's put, now we can put the buttons at the end. Put the buttons at the end. Let's put the back of the case. Here there are no screws anymore, right? DMX lamp, no, they're not. So connect earth first, although at this point it doesn't matter. Connect power afterwards. Ah, no, this is another thing. I think we need to put this. Yeah, it fits. It fits here too. Now we take the larger screwdriver. One. Let's not tighten them up yet. We'll do it afterwards. Let's first put the screws in. Up. Ah, I forgot to do something. I won't do it anymore. Clean up the flux residue. I wanted to do it, I didn't do it, so they will still be there. Well, they won't damage anything. They just don't look nice, but no one knows that they're here. Let's put the buttons back. The levels, I think they're called levels. Sliding, I don't know what. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, there was no marking, and this is no, they have no stop, so I can put them anywhere around. They are just encoders. Oh, that's too much. Okay, now it doesn't make any noise. That's better. Ah. Damn it. The metal is not really flat. Up. Ah, here we have indentations. Let's put it on the bottom. And let's try to screw it in. Oh, it's not as easy as it looks like. Do it from the top. Okay. Up. Not too tight. Let's do it from the bottom to the top, and we can do it on the sides. Up. One, 2, 3, 4. The screws. DMX. Let's start with these ones. Lamp and DMX output. Wrong screwdriver. Correct screwdriver. 1. 2. The camera doesn't show what I'm doing. Has the inputs, has the HDMI grabber. Okay. The HDMI grabber died. So now you don't see, wow, you don't see, I don't know if you even saw the soldering. Yeah, okay, yeah, Till, you're right. No, it's not intentional. Good that you said it. No, not at all. The grabber failed, the HDMI grabber for the camera failed. And I can't fix it. I think this is because of the USB hub, and when I connected on the things on it, I think it restarted the USB hub, and on this USB hub there was the HDMI grabber, and this failed. So no, it is not intended, and I cannot redo it without restarting OBS. So for this stream, it's dead. That's kind of a pain. I don't know how we can make OBS refresh everything. I'm gonna try to restart a stream on YouTube. I know on Twitch it creates a new stream. I don't know on YouTube if it's creates a new stream or if it continues this one. But yeah, you have to live with the overhead camera for now. So, and listen to my voice. All the screws have been connected. Let's connect power to it. Up, power. Power is on. The LEDs are blinking and it draws 4 watts. So let's switch back to the full screen, and I cannot change this. This is only the arm cam. No. And now I want to check that if we connect it, it still finds it. So original USB cable. Original USB cable. Let's connect the original USB cable, and we have some outputs right there. And we have the FTDI. So it still works. It is still enumerated. The USB is fixed. I don't know if anything else is broken inside. I don't think so, because it blinks and USB is enumerated, but I don't have any software to test it. But normally, the owner of this device will be able to pick it up tomorrow and test it. And then he can tell me if this is fixed, and he can avoid paying a lot of fees to have this repaired, because this wasn't under warranty. But for now, this is the end of the stream. It took, 3 hours. Wow. Yep, 3 hours of work, and this is fixed. So, owner, come by tomorrow morning. pick it up, and then you can tell me if it works or not. But for now, this is the end of the stream. Woohoo! See you soon, people in the chats. Bye bye. Enjoy.